had already started this topic in the last lecture, 33rd lecture, which started with FIR lattice design for the various situations of linear phase filters, and then we went to nonlinear phase filters with highest power coefficient equal to +1 or -1, and we saw that they could be synthesized with advantage if you decompose them into linear phase linear phase and a nonlinear phase filter, which can be realized by using taps on the linear phase structure. Then we started the impulse invariant IIR filter design. The philosophy was very simple, that is, we take an analog filter HA of S, we derive the HA of T by inverse Laplace transform, then we sample this, we sample HA of T to get HA of NT, which we accept as the impulse response of the digital filter. And therefore, if we take the Z transform, we get the transfer function H of Z. This is the route that we follow. That is, we first take the impulse response, sample it, and then the sampled impulse response we accept as the impulse response of the digital filter. We take the Z transform to get the transfer function. So the impulse response is invariant. In other words, if the sampling is done properly, then you can go from HA to HN or HN to HA reconstruction. But then, because HA of S is hardly ever band limited, capital T is never high enough to avoid, not high enough, capital T is never small enough to avoid aliasing. Capital T small means sampling frequency is high. As the sampling frequency goes up, aliasing distortion goes on decreasing. We shall show an example. So this is what impulse invariant transformation is, and we saw that all that we do is we expand HA of S in partial fractions, and if there is a term like this, then this goes to, in the Z domain, this goes as e to the power PIT Z inverse. In other words, we take care of the poles, but we cannot take care of the zeros. The transformation obviously is S equal to Pi goes to Z equal to e to the PIT, therefore the transformation is Z equal to e to the ST, and we showed that this is a stable transformation. In other words, if in the S plane we get a stable filter, stable HA of S leads to a stable H of Z, because the left half of the S plane maps onto the unit inside of the unit circle, the j omega axis maps onto the unit circle, and the right half of the S plane goes to outside the unit circle. So it's a stable transformation. In other words, H of Z should be a approximation to the desired digital filter. Now the question that I asked in the last lecture, does it guarantee, if impulse is kept invariant, does it guarantee that other responses are also invariant? The answer is no. To be able to demonstrate this, let us compare the step response of two filters. One is derived in the usual manner, that is starting from the analog filter. What is the step response? 1 by S HA of S, unit step response, agreed? Unit impulse response in the frequency domain is HA of S. The Laplace of unit step response is HA of S multiplied by 1 by S. Okay. Then we expand this into partial fraction, that is 1 by S minus pi, okay, summation 1 by S multiplies each term in this summation. Do you understand what we are doing? We are trying to find out the unit step response of this transfer function and then sample that to get the step response of the digital filter. All right. Okay. So this becomes equal to if you take the partial fraction equal to I should have added a residue S sub I divided by S minus pi. You can make this into the sum of two terms, 1 over S minus 1 over S minus pi. Agreed? 1 by S minus pi can be written like this. 1 by pi I have brought here, okay? And therefore the unit step response, which I shall call as psi A of t, shall be equal to summation A sub I divided by P sub I.
So it could be minus or minus CI by PI.
That is right. Thank you. Thank you for pointing this out. This is what it would be. Yes, you are right. S minus S plus pi. Agreed. So S sub I by pi, then you get e to the power pi t corresponding to this term minus 1 ut. Agreed? Is that okay? This is the unit step response. Now I want to see if we sample this, then we shall get a step response of a digital filter. Okay, that is, if we sample this, psi A n t shall be equal to summation A sub I divided by P sub I e to the power pi n t minus 1 u of n. Okay. This is the step response of the filter derived from an analog filter HA of S. We want to see whether this matches the unit step response of the digital filter that we derived from impulse invariance. Okay. From impulse invariance, what was our digital filter? Our digital filter was summation A sub I divided by 1 minus e to the pi t z inverse. Agreed? This was our digital filter. This was h of z. Now if you want to find out the unit step response of this digital filter, then what do? You multiply by the z transform of unit step. What is the z transform of unit step? 1 by 1 minus z inverse. Therefore, if we call that as psi, capital Psi of z, that is the z transform of the unit step response, then this would be equal to A sub I divided by 1 minus e to the pi t z inverse multiplied by 1 minus z inverse. Do you understand what we are doing? Okay. This is the digital filter that we derived from impulse invariance. We want to find out the unit step response of this. We have already found out unit step response of the filter derived from the analog filter, and we want to compare the two, whether if they are identical, then step invariance is implied by impulse invariance. If they are not, then impulse invariance does not ensure step invariance. Okay, so we want to compare this. Now, so what we have to do is now to take the inverse Z transform of capital psi of Z. That will give you the unit step response of the impulse invariant design. Okay, so let's find that out. Psi of Z is equal to summation A sub I divided by 1 minus e to the pi t Z inverse multiplied by 1 minus Z inverse. That can be written in partial fractions as I have done that. A sub I divided by 1 minus e to the pi t multiplied by 1 minus Z inverse minus e to the pi t divided by 1 minus e to the pi t Z inverse. Please verify if this is correct. You see, denominator is guaranteed. So 1 minus pi t Z inverse minus e to the pi t plus e to the pi t Z inverse, and therefore I have taken this in the denominator. Okay. So what remains is to find out the inverse transform of this. That would obviously be ai divided by 1 minus e to the pi t. The first term is 1. Okay. This is the unit step. I shall multiply by u of n, of course, and the second term is e to the pi t. This is a constant multiplied by alpha to the power n. Therefore, I shall get e to the pi t n plus 1. Okay? Agreed? This is the step response of the impulse invariant design. I compare now this with psi a of nt, which is summation let me get the expression ai by pi e to the pi nt minus 1 u of n. Is it obvious that the two are not the same? These two are obviously not the same. Therefore, impulse invariance does not imply step invariance. To be a little more confident about this, let's evaluate this for some values of n. Let's say n equal to 0. Then what is psi of n? Psi of n is equal to summation. Let's take an example instead of the general formula. Let's take an example. Suppose HA of S is equal to 1 by S plus 1, the first order Butterworth or Chebyshev filter. Then for this, psi of n obviously shall be equal to, yes? Do you have to put in the formulas or you can do it directly? Psi of n is 1 minus e to the t n plus 1, because pi, it is minus t. Be careful. Pi is minus 1. We had taken earlier, what did we take? S minus pi. Now we have taken s plus 1, so pi is minus 1. It has to be divided by 1 minus e to the minus t. And what would be psi a of nt? This would be 1 by pi is minus 1. ai is 1, pi is minus 1, and therefore it would be 1 minus e raised to the minus nt. All right. Obviously, these two are quite different. Quite different. For example, n. Let's list the values psi a of nt. If n is 0, then obviously psi a is 0. Isn't that right? If n is 0, then psi a nt is equal to 0. But what is psi of n? It's equal to 1. If n is equal to 1, if n equal to 1, then this is 1 minus e to the minus t. What is this equal to? If 1 plus e raised to the minus t. Therefore, psi of n is not equal to psi a of nt. In other words, impulse invariance does not imply step invariance. Okay. If we wanted a step invariant filter, if we wanted to design a digital filter in which the step response remains invariant, then obviously what we have to do is we take psi a of nt, which we have already derived to be summation a sub I divided by p sub I e to the pi nt minus 1 u of n. We have already derived. This is the sampled step response of the analog filter whose transfer function is HA of S, and we want this to remain invariant, and therefore we should derive a transfer function from this step response. All right. Now, if this is psi a of nt, then what is psi a of z, capital Psi? Take the Laplace transform. I am sorry, take the z transform. I get a sub I divided by p sub I 1 by 1 minus e to the pit z inverse for the first term, and for the second term I get 1 minus z inverse. Agreed? Now this must be the impulse, the transfer function h of z multiplied by 1 by 1 minus z inverse. Agreed? Therefore, the step invariant transformation gives me a transfer function h of z which is equal to summation a sub I divided by p sub I. What do I get here? 1 minus z inverse divided by 1 minus e to the pit z inverse minus 1. This is the transfer function that we get. And if you simplify this, then you get summation a sub I divided by p sub I e to the pit minus 1 z inverse divided by 1 minus z inverse e to the pit. It's not very complicated. This is a constant, e to the pit minus 1 ai by p. It's a constant multiplied by z inverse divided by 1 minus z inverse e to the pit. Let me write it again. Step divided by p sub I. Then let me collect the constant term, e to the pit minus 1 divided by pi, and the z inverse divided by 1 minus z inverse e to the pit. Have I made a mistake? Twice? Where? In the denominator?
There are two PI's in the PI by PI, then again
Oh yeah. Okay. I beg your pardon. Yes. This would not be there. Okay. Now, as far as the z domain function is concerned, this is a constant. As far as the z domain function is concerned, you see this quantity can be written as 1 by z minus e to the pit, right? And what has it gone? It has gone from S minus pi. Is it S minus pi? Yeah. S minus pi, 1 by S minus pi has gone as some constant multiplied by z minus e to the pit. Agreed? In the step invariant transformation, this is what has gone. A constant, this constant is this, take ai. This constant is ai e to the pit minus 1 by pi, but as far as z domain function is concerned, s minus pi has gone as z equal to e to the pit. In other words, the pole at s equal to pi has gone to a pole at z equal to e to the pit. So what is the transformation then? E to the st, isn't that right? The transformation, this transformation is the same as in the impulse invariant transformation. Isn't it the same? How come the functions are different? How come the transfer function is not the same as the transfer function obtained with impulse invariance?
So don't you think it is from ai divided by s into s minus pi from to k divided by z minus? It is that.
That's what we have derived.
No, so the transformation is from ai divided by s multiplied by s minus pi
That's right.
to k divided by z minus pi.
Yeah, but ultimately we have multiplied by 1 minus z inverse. We have obtained the impulse response. Impulse response is the same. Laplace transform is HA of S. 1 by S we multiplied to obtain the step response. Then we sampled the step response. We took the Z transform and then we multiplied by 1 minus Z inverse. Right? So ultimately a pole, a residue and a pole factor in the partial fraction expansion has gone into this.
Yes.
So the transformation is the same. If the transformation is the same, how come the transfer functions are different? Yes? The answer, isn't it obvious, the answer? What was the term in the partial fraction expansion of Hz obtained by impulse invariant transformation? Was there a Z inverse in the numerator? No. That is the only difference. In other words, the transformation is the same, but in the step invariant case, there is a 0 at z equal to infinity. In the other case, in the former case, there was no 0 at z equal to infinity. At z equal to infinity, this term became a constant 1. Do you understand? So step invariant transformation meddles with the zeros of the transfer function. And that is the difference. The impulse invariant. Pardon me?
Just repeat it.
Okay, let me, for the impulse invariant transformation, what was h of z? Can you, this was summation a sub I divided 1 minus e to the pit z inverse. Okay? Step invariant transformation, h of z is equal to summation a sub I e to the pit minus 1 divided by p sub I z inverse divided by 1 minus e to the pit z inverse. The poles are transformed according to the relation z equal to e to the st. But in this case, there is a z inverse in the numerator, which means that if z equal to infinity, then this term becomes equal to 0. 1 by infinity in the numerator, that becomes equal to 0. In the denominator, we get 1. Whereas here, there is no 0 at infinity. At infinity, it will simply become ai. So that is the difference. It's a very fine difference, but you should be able to answer why, using the same transformation, why the two transfer functions are different. One creates a 0 at infinity, the other does not. And that is the difference. Okay? let's go back. Similarly, you could get a ramp invariant transformation, okay, or any other function invariant transformation. But impulse invariant transformation is generally used in practice.
Excuse me, sir. What is the implication of 0 at infinity?
What is the implication of z? Well, it makes the transfer function different. If in each term you add a z inverse in the numerator, the transfer function is different. Okay? The implication in terms of frequency response is difficult to say because there is a summation, and these constants are important in the summation. Depending on these constants, you can get different transfer functions. So it's difficult to say what is the implication on the frequency response. But in the impulse invariant transformation, since HA of nt is equal to h of n, alright, how did we obtain h of n? We sampled the impulse response of the analog filter. Therefore, the frequency response of the digital filter shall be simply the summation of the frequency responses of the analog filter, okay, shifted by the sampling frequency. We have already derived this. This is equal to summation 1 by t, if you remember, summation h sub a of j omega plus j, yes, j 2 pi k by t. K equal to 0 gives the basic spectrum, k equal to 1 the spectrum on the left, k equal to minus 1 the spectrum on the right, but they repeat after omega, small omega, equal to twice pi. The relationship between capital omega and small omega is capital omega t equal to small omega, right? So by sampling theorem we know the spectrum, and this is how aliasing is obtained. If capital H at j omega is not band limited, now let's take this ideal case. If capital H of j omega is equal to 0 for omega greater than omega h, okay, if there is a highest frequency beyond which the spectrum is 0, where omega h is less than, omega h t is less than come on, our baseband is 0 to pi. Omega t is small omega, baseband is 0 to pi. So the spectrum must end at omega h t, and omega h t must be less than pi, must be less than pi.
Sir,
Okay?
mod omega is greater than.
Mod omega, okay. Omega h t should be less than pi. Is that clear? What I want is the following. Obviously you do not recall the diagram. This is omega pi. So the first spectrum, if it comes like this, it must end at some point, omega h t, and omega h t must be less than pi. Then pi plus omega h t, there will be another spectrum like this. Now if omega h t is not less than pi, then obviously we are asking for aliasing, right? So sampling frequency should be so chosen with due respect to the sampling theorem, and omega h t should be less than pi. If this is true, then there is absolutely no problem with impulse invariant transformation. If this is true, then h of e to the j omega shall be equal to 1 by t h a of j omega, where omega t, omega is less than equal to omega h, alright, and omega h is less than, yes, capital T divided by, I beg your pardon, pi divided by capital T. Why is it being so difficult, going from capital omega to small omega? It's very simple. Small omega is capital omega multiplied by T. If this is true, if the analog signal, analog transfer function is band limited, then our impulse invariant transformation will work beautifully without any problem. That is h of e to the j omega. We are only concerned with the baseband. It would be equal to 1 by t, only the first one, h a j omega, with mod omega less than equal to omega h less than pi by t. In the rest of the baseband, that is omega h t to pi, the spectrum shall be equal to 0. Agreed? If this is the situation, this is an ideal situation never obtained in practice, and therefore we have to take care. But it is important to realize that even if you get the ideal case, we have a problem in practice. The problem is h of e to the j omega is 1 by t h a of j. Instead of capital omega, can I write in terms of small omega? Small omega by t. Even if the original spectrum was band limited and sampling was done according to the sampling theorem, you see, when capital T is small, that is for a high sampling rate, even if capital H A j omega is normalized, normalized means the maximum amplitude cannot exceed unity, maximum amplitude is 1. The maximum amplitude of the digital filter transfer function shall be very large when capital T is very small. That means that there shall be definitely problems of overflow. Agreed? We cannot allow this signal to grow indefinitely. You would like capital T to be as small as possible. That is sampling frequency as high as possible to avoid all aliasing. Okay? But on the other hand, this raises a practical problem. That problem is that of overflow, because the signal is magnified with a very large constant, 1 by capital T. And therefore, what is done in practice, if you have to use impulse invariance, then you multiply the impulse response, usual practice. We multiply the impulse response of the analog filter, sampled impulse response, by capital T. If I do that, then h of e to the j omega shall be equal to h a of j omega by t in the baseband, and there shall be no problem of overflow. Agreed? So you take, the step is, you take the analog filter, obtain its impulse response, sample the impulse response, then multiply by capital T, and then take the Z transform. Alright? So capital T shall occur in whatever we have derived h of z, it is to be multiplied by capital T. In other words, h of z for our digital filter would be ai t divided by 1 minus e to the pi t z inverse. Is that clear? This is a step, this comes from practical considerations. People wanted to use this in speech processing and found that unless they do this, they always have an overflow problem. So simple simplification, simple artifice is to multiply the impulse response by capital T. This is a matter of discipline and it has to be done.
So, but in this case, the coefficients will be multiplied by capital T. That is very small.
Coefficients will be multiplied by
HN
capital
will be multiplied by capital T.
Yeah,
So
that's not
accuracy
a-
will reduce.
That's not a problem. If you don't want capital T, multiply by 5t. You see, increasing the signal is not a problem. You simply shift, then it's doubled. Okay?
Increasing
So
is no
capital
problem,
T-
But the accuracy is reduced.
No, you do this first. You don't multiply by capital T, multiply by twice t. You can do that. But the design is done so that the maximum amplitude does not exceed unity. Okay? That is the design. After that you can adjust according to your capability of the hardware. Okay, now I think that it is an appropriate point to tell you what happens if you have repeated poles. Our derivation so far has been for distinct poles, that is HA of S. We said that it can be decomposed into AI divided by S minus Pi, I equal to 1 to n. If a pole is repeated, well, we have also said that 1 by S minus Pi goes as 1 by 1 minus e to the pi t z inverse. Not quite, you have to multiply by capital T. Okay? I will repeat as many times as possible so that you don't forget this. Okay, now what happens if I have 1 by S minus Pi to the power m? If the pole is repeated, then the corresponding factor, it can be shown. You will thank God if such a repeated pole does not occur, because it requires considerable amount of algebra differentiation to be able to get this done. Minus 1 to the repeated poles always pose a problem, isn't it? Even in partial fraction expansion. Minus 1 to the power m minus 1, then divided by m minus 1 factorial, differential coefficient m minus 1 d pi m minus 1, then 1 by 1 minus e to the pi t z inverse. No, not quite. Yes. Okay, do not forget this, then you will make a mess, your filter shall not work. Okay, so this is what happens if you have repeated poles. And as you know, if you have repeated poles, then it does not end up in one component in the partial fraction expansion. It requires m number of components. You shall have some constant divided by s minus pi to the m, another constant divided by s minus pi to the m minus 1, up to s minus pi. And every time you shall have to do this, okay? I have not found a shortcut to this. If I find, then I will let you know. Two other useful transformations, that is, if you have complex poles, then you don't want to transform each complex pole factor, because this results in complex coefficients. You would like to transform the two together, complex pole and its conjugate pole. And the situation that occurs is, if you have a pair of complex conjugate poles at minus a plus minus jb, and the numerator is s plus a, then this goes as 1 minus e to the power minus at cosine bt. It can be very simply derived. You expand this in partial fraction, two partial fractions, transform each term, then add the two and simplify. This is what you get. 1 minus twice e to the minus at cosine bt z inverse plus e to the minus 2at z to the minus 2. Okay? So you know what 1 by s minus pi goes as, you know what this goes as, and the other thing that you require is b divided by, that is if the numerator is a constant. It's not a linear function of s. If it's a constant, s plus a whole square plus b square. Remember, this b is the same as this b. So if the numerator is not b, then you have to bring b by scaling. Alright? So this goes as e to the minus at. You can guess correctly, it is sine bt z inverse divided by the same denominator.
Won't we multiply by t?
Yes. You have to multiply by t. Yes. So what you do is, you don't do this piecewise. What you do is, you take h of n as capital T multiplied by h of nt. Then you expand, then you take the z transform, obtain this, obtain that, and so on and so forth. Okay? So you don't have to do this every time. You don't have to do this every time. We'll take an example now. Fairly illustrative example. Our example is a third order low pass Butterworth function. You know it is s plus 1, s squared plus s plus 1. Alright? And the partial fraction expansion is 1 by s plus 1 minus s square plus s plus 1 and s. You can verify this. S square plus s plus 1, then minus s times s plus 1. So the numerator will be 1. If you are not sure, put it in as plus b and then find out a and b. Okay. So I can write this as 1 by s plus 1. I want to use those two transforms. So what I do is minus, I write this as s plus half. Oh, the denominator I can write as s plus half whole square. I have to bring this term plus root 3 by 2 whole square. This gives you 1/4 and this will give you 3/4. So 1/4 plus 3/4 is 1. In other words, I identify my a as half and b as root 3 by 2. And s I write as s plus half minus half. Okay? So I can write HA of s as equal to 1 over s plus 1 minus s plus half divided by s plus half whole squared plus root 3 by 2 whole squared plus, not minus, minus and minus makes it plus, the same denominator. I don't want half, I want root 3 by 2. So multiply by 1 by root 3. Agreed? And now I am quite comfortable. My transfer function, therefore, h of z, this is the point where you multiply by capital T. So you say h of z by capital T would be equal to, now take it term by term, 1 by 1 minus e to the minus t z inverse, then minus 1 minus e to the minus t by 2 at, then cosine bt, that is root 3 t by 2 z inverse divided by 1 minus twice this term e to the minus t by 2 cosine of root 3 t by 2 z inverse plus e to the minus t z to the minus 2 plus 1 by root 3, this should be e to the minus t by 2 sine of root 3t by 2 is the inverse, the same denominator. I have obtained the transfer function. Obviously, you can bring these two terms under the same denominator. Then you can put z equal to e to the j omega and find out the frequency response. Okay? The frequency response that I want is a third order Butterworth low pass response. And if it is identical with the analog response, then my job is done. Right? If it is not, then I have to do something. Now look at the frequency responses that I plotted. For this filter, you should read this carefully. This is the analog filter. This is the third order Butterworth analog filter. Okay, what I have plotted here is versus small omega. Small omega is capital Omega multiplied by capital T. Now obviously the transfer function depends on capital T, right? Capital T. If you sample at a very low frequency, well, you are asking for trouble. You have to choose a good high frequency sampling. You see, if capital T, the sampling interval, is as large as pi seconds, 3.14, this is what you get. In your wildest imagination, this is not a low pass filter, isn't it? It's a band pass filter. Okay. And then capital T 2.09, that is we reduced the sampling interval. This is what we get, this triangle. This is also not a low pass filter. Okay. The rejection is very poor, 0.6, also it has overshoot in the frequency response. Then again it goes up. But with capital T equal to 0.25 seconds, what is the sampling frequency corresponding to this? 0.25 second? 4 hertz. Why is it so small? 4 hertz is not a practical value, because we took a normalized analog filter whose cutoff was at 1 radian per second, and therefore 4 hertz is a good enough frequency. 4 hertz, and you see the plus sign, that is, it's indistinguishable, almost indistinguishable from the analog filter. Okay, you shall have to do this if you want to work with impulse invariant filter. Then you have to use a MATLAB to be able to draw or watch on the monitor the transfer function, frequency response, and you adjust your capital T in such a manner that you get a fairly good match with the given analog filter. Of course, if you continue this, you see what is the value here, 3. If you continue beyond pi, then the analog filter and the digital filter will differ considerably. What will happen beyond pi? This will rise. Is that right? Our digital filter frequency response, we are happy to be confined to the baseband. If we go beyond 3.14, obviously it would rise like this because it's periodic. We are not concerned about that. We are concerned with the match only in the baseband. Okay?